seems like a lot, like if I asked you to add up the first 1,300 numbers. But we've got to go to infinity, right? And that means 1,300 is nothing compared to infinity. So maybe this does grow just very slowly, and just eventually it just, just keeps getting bigger and bigger and bigger, and it just overflows. Does that make sense? Now, turns out this one does converge though, all right? The first one I showed you, 1 over n, the series for that diverges. This one converges. But I still haven't proven why, right? I still haven't explained why. You're just going to have to take that on faith right now. So the main idea at this point is the following. If you have a sequence and you try and find the infinite series that corresponds to the sequence, it's either going to converge or diverge. The way you check to see if it converges is by taking a limit of the partial sums. So this is the thing we're most interested in. Can we find the limit as n goes to infinity of s sub n? Does this limit exist? Does this turn into a number or not? Right? Does it? Compare that to this. This is what we did last class. This was just asking us to find the limit of the individual term or number within a sequence. This is asking us to find the limit of the sum of all the terms. All right. Now, because it's so challenging to do this, like I said, in general, if someone just gives you a series and says, hey, does this converge or diverge? Because it's so challenging, we start this investigation by looking at the most common series first. After we get the most common ones out of the way, then we start trying to use special techniques to handle the ones that are more complicated. And there's going to be a bunch of tests that we do in order to determine convergence or divergence. All right? So let me start with the common series. And I'm going to put these up in just the order that I think they appear in the book, but I'm not necessarily going to cover them in the order they appear in the book. The first most common series that you see out there is what's called a geometric series. So what we're doing is when we look at series, we say, hey, does that series behave a certain way? It's kind of like when you look at a quadratic. We all know what quadratic functions look like, right? It's like you look at them and you see it and you're like, yeah, that's quadratic, that's a parabola. Same thing with series. When we look at them, there's a way we can look for certain things and say, oh, that's a geometric series. So we're going to look at those first. After that, we're going to look at what are called harmonic series. We're going to look at p-series. And finally, we're going to look at telescopic, or another word for this, you'll hear me using this, collapsing. Telescopic or collapsing series. Now, I've got good news and bad news when it comes to these series. Well, it's actually all good news. For geometric series, all geometric series, when you look at them, they are either going to converge. I'm going to use C for converge, all right? So I don't have to write converge over and over. A geometric series will converge or diverge. You're going to have to figure that out. And we will spend some time here determining how it is that we can tell if a geometric series converges or diverges, all right? Additionally, if it converges, right? If it converges, we will know S. Now, what is S? The sum. We will actually, not only will I be able to tell you that it converges, I will actually tell you what it converges to. So if you were able to add up all the pieces forever, I will tell you, we will be able to say what it would add up to be. So that's very nice. Harmonic series always diverge, all right? So if you look at a series and you say, okay, it has these characteristics, which I'll tell you what they are later, you go, oh, it's harmonic. It diverges. There's no work that has to be done. You just have to be able to identify it's harmonic. A P-series will converge or diverge. Bad news, though. I won't be able to tell you what S is. Can't find what S is. If it converges, right? If it converges, I will only be able to tell you that it converges. I will not be able to tell you what the actual sum is. And that may bother you. You may be like, well, you know, we want to know the sum. Well, it turns out as we progress through this chapter, really at the end of the day, the convergence or divergence is the most important thing to us. All right? All right. Questions so far?
So you can't find S if it converges. What if it doesn't?
If it diverges, it diverges. That means there is no sum. The sum doesn't exist. It's infinite or something weird. Like there's a very common series. Look at that series right there. And we're getting a little ahead of ourselves. But what do you think that series does? What's 1 minus 1 plus 1 minus 1 plus 1 minus 1? Diverge? So why do you think it diverges? Any? So when I've said diverges in the past, a lot of students associate divergence with infinity. Do not associate divergence with infinity. Divergence means not convergence, okay? So convergence means it goes to a number. Divergence is every other possibility. So is this sum going to a number?
No.
Yeah, I mean, look at it. If I take the first sum, right, I get 1. Next one out, I get what? 0, 1, 0, 1, 0, 1. So as I go out to infinity, is that sum headed to a particular value? Doesn't appear so. It looks like it's oscillating. Now, you could make an argument maybe like take these, just these. Look at just in red. Leave the 1 out there. Okay? These should cancel. These should cancel. These should cancel. And they cancel the whole way out there, and so you just have 1. Basically, this is not, there's different ways to look at it. You're going to get different answers depending on how you look at it. So, but it doesn't go to one place, all right? Does that kind of make sense? All right, we're getting a little ahead of ourselves. So divergence in the P-series, if it converges, then we won't be able to say what it adds up to be. Telescopic is either going to converge or diverge. And there is some good news here. If it converges, we will know what S is. So you have a test in a week, right? This topic will be on that test. And one of the things that I'll probably ask you is to find the sum of a series. Okay, so I'll give you a series and I will say, find the sum. Can anybody tell me, just from what we've talked about so far today, what that problem sitting in front of you must be then? Either a geometric series or telescopic, right? Because if I ask you to actually find the sum, I'm implying that you're able to get this. And the only way you can get this is if it's a geometric series that converges or collapsing that converges. Understand? That's a hint on the test. If you see find the sum, then you know it's either geometric or collapsing. If it says, does this converge or diverge, well then it can be any of these, right? All right, so let's get these common series out of the way. We won't finish this today, but I'll see how far I can go. And we'll start with geometric. very famous type of series, the geometric series. Here is what a geometric series looks like. All geometric series look like this. You have A times, A plus AR plus AR squared plus AR cubed plus AR to the fourth plus ... forever. So what does every single one of those terms have in common? They all have an A, right? And then attached to them with multiplication is some number, right, R, raised to a power. And that power keeps on going up by 1. Also, make note here that this first one is actually A times R to the 0, right? That's really what that is out there. That's what a geometric series looks like. Now, we looked at this series earlier. Is that a geometric series? Well, the thing that's changing up here, right? The thing that keeps changing in each one of these terms is the exponent. Do you all agree? Like we have an exponent here of 1. Here it was R to the 0. So A and R stay the same, but we're changing the power from 0, the next one 1, the next one 2, the next one 3. So in a summation notation like this, the n that's changing needs to be somewhere in the exponent of a number. Is this n in an exponent? No, it's not. So this automatically is not geometric. Now let me write this formula in sigma notation or using a summation. Why don't you help me out on this? Sum n equals 1 to infinity. Can you create that list with a formula right here? A, R to the what?
N plus 1.
Close, n minus 1, right? So if I plug in 1, I get 1 minus 1, I get 0. So it's A times R to the 0. That would be my first one. Then I let n be 2. That would be 2 minus 1, that's 1. So you get the next piece, right? This is like the granddaddy formula for geometric series right there. So the question is, does it converge or diverge, right? Does this converge or diverge? C means converge, D means diverge. That's tough, right? I mean, you can't add this up forever. So we are going to find a way to do it. Before I actually do it, though, let me give you an example, a specific example of a geometric series. So you can kind of see it in action. 3 plus 3/10 plus 3 100ths plus 3 1,000ths plus 3 10,000ths plus ... That's an example of a geometric series. So can you tell by looking at it what the A is? Looks like A is 3. But if A is 3, what's your R? So let me try and rewrite this for you. 3 plus 3 times something plus 3, well, it's supposed to be 3 times something square, not squared, to the first power. And then 3 times something squared plus 3 times something cubed plus 3 times something to the fourth plus 1/10. Does everyone see that? 1/10 here, 1/10 to the first power is going to be 3/10. 1/10 squared is 1 100th times 3 is 3 100ths. 1/10 cubed is 1 1,000th times 3. And then last one, right? Oops, 10. And that first one, there really is sitting here a 1/10 to the 0, right? So in this geometric series, what's A? So this is geometric. A is 3, and R is 1/10, right? All right, so all geometric series look like this. This is a sigma notation for it, and that's a specific example. Here's another sigma notation. Actually, I'm going to put it here, and I'm going to see if you can give me the formula. I've always told you to start sequences out at 1, haven't I? I've always said that. But I think when I first said that, I said there's going to be a point where we want to start it maybe somewhere else. And I said 0 might come into play. So can you create the same series using n equals 0 to infinity instead? Like, how would your formula here change? A times r just to the n. You don't need the n minus 1 anymore, do you? Because if you plug in 0, you just want 0 on that first power of r. And then when you go to 1, you'll get your next piece, and then 2. Okay? So these are equivalent. These create the same exact geometric series. The book will switch back and forth between the two notations. And at some point, we're actually going to use this one more than this one. But you should be comfortable with both. All right, that's what a geometric series is. And now we go and try and figure out if we can determine if they converge or diverge. What did I tell you they would do? What did I tell you geometric series would do? It would do either one, right? Oh, by the way, if you have that take home, yeah, just kind of pass them, get them like at each table, and then kind of somehow get them. Let's try and get them all to this table. All right, my question is, does this series converge, right? Does this series converge? And if you look back at your notes from just a minute ago, I said if a series converges, then the limit of the partial sums will go to S, won't it? That's what I said. It'll go to some number. That's what it means to converge. So let's try and take this limit. Ooh, that's nasty. That's nasty. So how about this? Hold off on that. Now what I'm about to show you, somebody came up with, not me, all right? I'm just here to show it to you, and it's pretty awesome, all right? So someone was trying to figure out how to actually get this geometric series. So they said, look, let me start out by looking at the nth partial sum. What would adding up the first n of these look like? So they said, all right, well, that's a plus ar plus ar squared plus ar cubed plus dot, 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 dot. But I'm stopping, right? Stopping ar. Think about it carefully here for a minute. It's not n. I'll help you with this. S1, what would S1 be? What would the first partial sum of this series be? A. Okay. What would the second partial sum be? A plus AR to the first power, right? What would the third sum be? A plus AR plus AR what? Squared. So what's the relationship between this number and this number? It's one less, right? This is one less than this. So this is going to be r to the n minus 1. Okay, does everyone agree that this is the nth partial sum? Yeah? Okay, I'm supposed to take the limit as n goes to infinity and stick it in front right here, right? The problem, this is what I was trying to illustrate, the problem is if I take the limit as n goes to infinity, this piece takes off, right? My sum gets larger. What I would prefer to have is a nice packed-in formula that doesn't require me adding up a bunch of things. So what do? Well, somebody said, let me try this. Let's rewrite this sum, but let's just multiply the sum by r, okay? This is not something you would just like, oh yeah, sure, just do that. I mean, this is, somebody thought, okay, maybe just try it. So what would happen if I multiply this sum by r? I just multiply every single one of these by r, don't I? So multiply this by r, and what would I have? AR, next one. AR squared, next one. AR cubed. what would my last one be? AR to the n. I'm going to leave a space right here. Make your last one right here. AR to the n. So basically, by multiplying everything by r, the powers on all of these r's came up by 1, right? And so this one, you just add 1 to that and you just get n. Agreed?